Okay, continuing on with our sample test here. Moving on to question number 4. Oh, some weird shadows going on there. Maybe do it like that. That looks a little bit better. Maybe this light can come on. Okay. So number 4 here, we want to calculate. Right, so if you're tired of naming, don't worry, we'll get to calculations as you go through the test. How many atoms are in 45.00 grams of NH3? So NH3, that's a neutral compound that's called ammonia, right? Not really one of the ones we've talked about naming so far. But this is going to be essentially a unit conversion problem. We need to take the data we're given to start the problem. We need to work our way to the answer. So if I start with 45 grams of NH3, it'll help if I write it correctly, 45.00 grams of NH3. Right? What I want to do, or at least a good strategy here, is to let the units kind of guide you through solving the problem. Starting with grams here, the first thing I want to do in this next fraction is cancel out grams of NH3. So I want to put that on the bottom. Now, if I'm thinking about getting to atoms, I head in the right direction if I convert to moles of NH3. Now, grams per mole of NH3, that's the molar mass. I can find that in the periodic table. So if I go to the periodic table, I can look up the molar mass of nitrogen, and I also have 3 hydrogens in this molecule, so I want 3 hydrogens as well. So nitrogen is 14.01, hydrogen is 1.01, and we're going to multiply that by 3, so that would be 3.03. So 17.04 is the molar mass of NH3. Right? So 1 mole of NH3 would weigh 17.04 grams of NH3. That would successfully cancel out grams of NH3 there in our units. What we have now is moles of NH3. So next step, right, I want to cancel out moles here on the bottom. And I want to think about what can I relate that to that gets me closer to atoms. Now, NH3 we would classify as a molecule, right? There are multiple atoms in there. There's a nitrogen atom, there's 3 hydrogen atoms. So what I can do is I can relate a mole of NH3 to how many molecules of NH3 are in that sample. And this is Avogadro's number, or the Avogadro constant. 1 mole of NH3 would be 6.022 times 10 to the 23rd molecules of NH3, and I did not do a great job of leaving enough space for that, right? But remember, that's all one number, 6.02 times 10 to the 23rd, just in scientific notation there. That step canceled out moles, and now we have molecules. Now again, that's not quite atoms, so the next step, and this will be the final one, so we are going to keep it on the video screen here. I want to cancel out molecules. So molecules of NH3 is what I'm going to put on the bottom. And what I need to do on the top is relate that to atoms, right? And it's not a specific type of atom, it's just total atoms in the molecule. So looking at the formula, NH3, that's 1 nitrogen, 3 hydrogens. So every 1 molecule of NH3 contains 4 total atoms. That would cancel out molecules, leave me with the units I'm looking for, which are total atoms, or number of atoms. So now I can just punch this into my calculator. So 45 divided by 17.04 times 6.022 times 10 to the 23rd times 4. And so what I got here is 6.361267606 times 10 to the 24th power. Now looking back at all of the information we had up here, we start with 4 significant figures, exact. This is a definition, so these are exact, right? And this is countable, right? You can count how many atoms are in that formula, so those are all exact. So our answer should be 4 sig figs here. So it would be 6.36 and then I get one more, and I don't have to round up, so 1 times 10 to the 24th power. Okay, so I'd be prepared for a similar type of problem to that one, right? Make sure you know your Avogadro's number, make sure you kind of understand where to find this type of information with molar mass in your periodic table. All right, let's see if we can fit the next problem into this video. We're at about the 5-minute mark, so we've got about 5 minutes. That's probably all right. Okay, an oxide of tungsten is a bright yellow solid. 5.34 grams of the compound contains 4.23 grams of tungsten. What is the empirical formula? So empirical formula, that's the ratio of tungsten atoms to oxygen atoms in this particular compound. So what we want to do is take this mass information and figure out how many moles of tungsten or oxygen are present. Now, if there's 4.23 grams of tungsten, that's where we can start calculating how much tungsten is present here. But the other thing here that we're going to have to figure out is how much oxygen is there. So the problem tells us how much tungsten there is and how much of the total molecule there is. So the 5.34, that's tungsten and oxygen. Right? We don't know the ratio yet because that's what the empirical formula is. If I subtract how much tungsten there is, right, that will leave me with how much oxygen is in the compound. So 5.34 minus 4.23 is 1.11. So there's 1.11 grams of oxygen in this compound as well. So I'm also going to want to figure out how many moles of oxygen would be in that sample. So starting from both those masses, I'll go to the periodic table, right, and I will find the molar masses of each of these. And you might want to call it an atomic mass since these are both elements. So tungsten is 183.84. So I'll divide by 183.84 there. Oxygen is 16.00, so 1 mole of oxygen is 16.00 grams of oxygen. Right? And if I work that out, that'll give me how many moles of each were used in this sample. So 4.23 divided by 183.84. And my tungsten is 0.02301. Right? Now we really had 3 sig figs to start with, so it's okay if you just go to 3 sig figs. I went to 4 here. Right? Remember, we're looking for integers here with empirical formula. So as long as you keep enough that you don't throw off your integer ratio. 1.11 divided by 16 would be 0.0693, and it's 7.5 exactly in my calculator. So instead of rounding there, I'm just going to write that one all the way out. This one went quite a bit further. Okay, that's moles. So this is moles of tungsten. This is moles of oxygen. Now, we of course know the other thing we need in an empirical formula is we need these values to be integers. So the last step here to get to the empirical formula is to turn these into integers. So whichever one is smaller, and that's the value for tungsten, we're going to divide them both by that smaller value. So if I divide tungsten here by 0.02301, that will give me 1 mole of tungsten. If I do the same for oxygen, that'll keep the ratio the same, and hopefully that gives you an integer. So take my previous answer, divide by 0.02301, right? And it's very close to an integer, so 3.01499, right? So that essentially, the experimental error is 3 moles of oxygen. So if I have 1 mole of tungsten to 3 moles of oxygen, that means my empirical formula is WO3. 1 tungsten, sorry, I got a little bit off camera there. 1 tungsten to every 3 oxygens. Okay. Now, this would be a really nice question to add a little bonus question afterwards, which would be, what is the charge on the tungsten here? So WO3, 3 oxygens. We know each oxygen, when it's in the oxide form, has a -2 charge. Since there's 3 of them, that's a total of -6 from your anion. And that means this would be tungsten with a +6 charge, or this would be tungsten 6 oxide. All right, we'll end the video there. We'll come back for the next page of the practice exam in the next video.